Hi, it's Sue, and we're continuing with our videos for 3.1. This video is going to talk about how do you find the derivative of x to the n, where n is a positive integer. So we're going to dive right in with this, and we're going to use the limit definition of the derivative. So here we go. F prime of x, the limit as h approaches 0, f of x plus h minus f of x over h. So let's keep going. We know f of x is going to be x to the n. And we know that f of x plus h is going to be x plus h to the n. I'm going to make sure my n's don't look like h's. So normally what I would do here is I would multiply out that first expression and hope that the x to the n cancels out. But it's kind of hard to expand something to the nth power because I don't know what power that is. Except that you are brave and strong and true, and you do know how to expand out h plus x plus h to the n, because you remember the binomial theorem from pre-calculus. Yes, you do. Yes, you do. So let's go ahead and use that. In fact, we might need to go to the line below. So you recall, of course, that if you're multiplying out x plus h to the n, you're going to get a bunch of terms. The first term is going to have an x to the n. The next one will have an x to the n minus 1, and they will have decreasing powers of x. At the same time, the powers of h will increase. So your first term has an h to the 0, then an h to the 1, and an h to the 2. So let's put some of that in. Then, of course, there are coefficients. I'll leave a space for the coefficient. Now we're going to need a dot, dot, dot here, right? So our final term, let's do our last two terms. Our final term will be h to the n. And the term before that will have 1x and n minus 1 h's. Good. Now I don't want to forget my minus x to the n, so I'm going to put that in there. That's not part of the expansion, but it is part of my expression. Now you have to remember the coefficients. And a lot of times you get them from Pascal's triangle. So when you square something out, the coefficients are 1, 2, 1. And if you cube them out, 1, 1, 1, 2, 1. If you cube it, it's 1, 3, 3, 1, 1, 4, 6, 4, 1. But that's not really going to work here because I can't put specific numbers in because I don't know what specific number I'm doing. So instead, the other way of thinking of it, those were the combinations, right? So the first number is 1. The second number is, do you remember this? It's n choose 1, right? So the first number is always 1. The next number is always the number of the row. So in the fourth row, it's 4. In the fifth row, it's 5. So in this case, in the nth row, my coefficient is going to be n. Actually, you could also write that as n choose 1 if you wanted. Do you remember that? All right, but n choose 1 is just n, as I'm sure you recall. The next coefficient is n choose 2. The next coefficient is n choose 3. Blah, 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 blah. And then at the end, they reverse themselves, okay? So our very last one here, the h to the n, that's going to have a coefficient of 1. This one's going to have a coefficient of n. The one before that is going to have a coefficient of n choose 2. I didn't write that one down. Okay, so let's take a look at this hot mess and see if there's anything we can simplify or if this is just going to be a disaster. If nothing else, there's an x to the n here and an x to the n here. Those cancel out. And now I have all these terms left. This is a mess, right? But you might remember from our other problems that usually what happens is you can cancel out an h. And in fact, that happens here. You might notice that every term, no matter how gross it is going to have an h in it. At least one h in it. Is that true for all the omitted terms as well? Yes. Right? Because they go from having one h, an h squared, an h cubed, an h to the fourth. Every one of these is going to have at least an h in it, so we are going to divide that out. I'll put that in the next line. So my powers of h all go down by 1. So this exponent goes down to n minus 2. And this exponent goes down to n minus 1. And they all cancel with the h on the bottom, so really we just have a 1 on the bottom now. So now what can I do with this? I've gotten rid of the denominator. Can I go ahead and take the limit? I think I can. Because if I put in h is equal to 0, I will not get 0 over 0. It's going to be just fine. So as h goes to 0, let's see what happens to these terms. Let's see. This term goes to 0. This term goes to 0. This term goes to 0. They all have h's in them. Do all these terms in between also have at least one h? Yes, they do. So all these terms go to 0, and your final answer is going to be n times x to the n minus 1. This is a very powerful formula. In fact, let's write it nicely. So this says the derivative of x to the n is equal to n times x to the n minus 1. So here's an example of how you can use that. If I ask you what is the derivative of x to the 6th power, well, n is equal to 6 in this case. So your answer is going to be 6 times x to the 6 minus 1, or 5. Isn't that fast? So this is called the power rule. There's a place to put it here on the next page. In fact, I think it's written for you. And it actually turns out that although our proof is only valid for positive integers, because it depends on the binomial theorem, it turns out that one can do a proof for any non-zero real number. So if n is equal to 4.5 or negative 3/8, right, it's still going to work. So here's a different example. I could take the derivative of x to the negative 1/2 power is going to be negative 1/2 times x to the negative 1/2 minus 1 is negative 3/2. So you can do an enormous number of derivatives using the power rule. The next thing that you ought to do, and you'll probably go over this maybe in class, is try these following examples.